Now let's shift our focus over to analytical standards. Analytical standards are important in many methods, especially in methods that relate some concentration to a signal or an intensity that we're measuring. Generally speaking, we will need to measure the proportionality constant for these methods. Sometimes in other methods like gravimetric or titration-based methods, we will not have to do this because the proportionality constant is based off of a stoichiometry, but we still will probably need some analytical standards at some point. So, again, these are more important when we're talking about spectroscopy or electrochemistry, as in concentration-based methods, but they still get used in other methods. And I have an example of that when it's used in titration. So, if we want to have an analytical standard, we should know what are the characteristics that we want in a standard to be able to make accurate measurements. So, it is very, very important for a primary standard, and this is a standard that we will base other measurements off of. Right? We don't need any other check on these or confirmation of what this is. We can take this off of the shelf, measure it, and know this is exactly what it is. So in order to do that, we'll have to know the stoichiometry of any reaction that involves the primary standard. So, for example, if we were using KHP, potassium hydrogen phthalate, to standardize something, we would know that it would react 1 mole with 1 mole of a base, for example. So, it would produce, or it would react by releasing 1 hydrogen, or it could also react by absorbing 1 hydrogen. So known stoichiometry is very important. It is also very important that we know the purity of this standard. It should be, generally speaking, of a very high purity, but it's acceptable for it to be a lower purity as long as we know what that number is. So even if something was, say, 80% of something, if we knew that purity very accurately, we could still use it as a primary standard. These standards should be shelf stable. That is, we could put it on a stockroom shelf, leave it for quite some time, and it will not change composition. It will not react. It will not decompose during that time. Shelf stable. It should also be not hydrated. So, for example, something like copper sulfate pentahydrate would not be a good primary standard. And why is that? Because the waters of hydration can change over time when it's sitting on a shelf. It's just a lot easier for that to happen. And in the same vein, we should not have hygroscopic materials, especially when we're trying to weigh them out on a balance. If the material is particularly hygroscopic, it could be difficult to accurately weigh this out. And it's difficult to know exactly what the chemical formula is for that, because we have an unknown amount of hydration in the sample, which comes back to not hydrated. And I like to add one more. It's better to have a high molar mass for our primary standards. This is not a requirement, but it is convenient and it is nice to have a higher molar mass. And why is that? Well, that's because this allows us to weigh out a smaller number of moles for a given mass of substance. So you could say that a higher molar mass leads to a higher sensitivity for a given amount of mass, right? Because the slope for that will increase faster. Again, this is not required, but it is a nice feature if we can. And that is another added bonus for potassium hydrogen phthalate because it has a molar mass of around 200, which is relatively high in comparison to other compounds such as sodium chloride or sodium hydroxide, for example, which I believe is about 40. Now, let's talk about secondary standards. So we've talked about primary standards, and these are things that we know the composition of. We know that they're shelf stable, they're pure compounds, they don't pick up water. Now, we may want to use substances that don't have all of these characteristics, but are important to use in an analysis. Let's say, for example, a lot of times a titration would involve sodium hydroxide. Now, sodium hydroxide is hygroscopic, so it is not a good choice for a standard, or at least it is not a primary standard. We also don't know how much of it could have reacted with some carbon dioxide that came out of the air. So we're not exactly sure what the purity of it will be because, again, it could react. And if you've ever seen a container where somebody didn't put the lid on very tightly, then you'll notice, yes, it's hygroscopic. And when you go to weigh it out, it's not necessarily the case that you'll be able to weigh it before water from the air is being picked up. And all of this matters when we're doing analytical chemistry. So we'll use a primary standard to determine the concentration of a solution or a secondary standard. So, as an example, we want to use NaOH in a titration. But again, NaOH doesn't fit our characteristics of a primary standard, but KHP does. So we'll make our NaOH and we'll try to aim for approximately the concentration that we want. A lot of times it's 0.1. It's molar. It's a convenient concentration. And so we'll make approximately 0.1 molar. And then what we'll do is we'll measure out a particular amount of primary standard. In this case, we'll use KHP, but there are other primary standards that we could use, such as sodium carbonate or something like that. But we'll titrate it with that. We'll use our primary standard to determine the concentration of the secondary standard, and we'll in a process that's called standardization, and then we will have much more number of significant figures on our concentration here from that process, and then we will be able to use this solution as a standard. And that is an important aspect of standards, is the ability to take something that might not be the primary standard, but then standardize it so that we can use that substance in further reactions, because that may have characteristics in the analysis that we desire that it just didn't have all the characteristics in order to become a primary standard. One of the characteristics for this is the inexpensive nature of sodium hydroxide and how quickly it will react and function as a titrant in those cases. So that's a little bit about analytical standards.